Hi, this is an example problem from chapter 27. Pause for a moment to read the question. So you can see we have a little nice picture here of the single slit diffraction apparatus to kind of help us visualize what we're doing. And we can already notice a few things. So we know what the slit width is here. Notice that for a single slit diffraction we call the width W. So this is going to be our 3 micrometers right here. And we also have, just like we did for double slit diffraction, we call the distance between the slit and the screen L, in this case 2 meters. We also know what the wavelength of light is in this case, 525 nanometers. And we're asked in part A, find the position on the screen of the first dark fringe. So you can see that that's this position here, and the position on the screen, we want to figure out what Y is. What is Y? In this particular problem, this height, in other words. It says the first dark fringe. Let's figure out exactly what equations we want to use and how we label these fringes, these orders for the single slit diffraction. So we can go look at some notes here. Single slit diffraction. First of all, here is the equation that we're going to want to use here that describes, notice that this is the location of the diffraction minima. It's only the dark spots. There's no expression given for maxima in this class. We're only looking at dark spots with this equation. Again, we can always use the equation that relates the triangle that you can make between the slit, the screen, and the distance between the slit and screen. Now for single slit diffraction, notice that in the equation we start with m equals 1 as the very first dark spot. So when we label these, here's a picture. What we're saying is this right here, that spot, that's m equals 1. This next one here is m equals 2. And of course these are symmetric, so this is your m equals 1. There's your m equals 2. We're looking for the m equals 1 here. Let's go back to our problem. Let's go ahead and paste the equation that we want to use here. Now, for part A, find the position on the screen of the first dark fringe. So okay, we've got this equation, and we're trying to find, basically, if we think of this as a triangle, right? We've got this nice right triangle here. We want to find that short side there, the right triangle. We need to know what the angle is here, right? So we're going to be looking for this angle here. Call this one theta 1 we can for m equals 1. And we know what L is already, so we know that base. We just need to figure out what the angle is, then we can do Y. So to get this angle, we're going to work with the equation that we have here. So here's our theta, dark 1. I'm going to go ahead and got to take the inverse function here, and we are going to be left with this, which is going to be m lambda W. And we know all of those things, so we'll go ahead and plug in those values. M is equal to 1. Lambda is equal to 525. I'm going to go make this meters so that I have the same units easily for both. There's your wavelength. And finally, we're going to put in the slit width, 3 micrometers. That's 3 times 10 to the minus 6th meters. Our meters are going to cancel out, which we need. No more length units. We're good. Put this into the calculator, and we get a value equal to 10.07 degrees. And now we can use the geometry of the right triangle there to figure out what Y is. So Y is going to be equal to L times tangent of theta dark 1, which means that's equal to 2 meters multiplied by tangent of 10.07 degrees, which is equal to 0.355 meters. And that's our Y dark 1. Now for part B, it says, what is the highest order dark fringe that can occur under these conditions? So notice if we go back to the picture, we'll look at it for a second, right? This was our m equals 1. right? And as we go to higher and higher m values, we're going to be moving, further away. Some of these might not even hit the screen. So maybe this is, say, m equals 2, right? And we keep on going, right? Maybe over here. Notice the angle keeps on getting bigger and bigger and bigger as we do this, right? The angle is just increasing and increasing. Well, eventually we're going to get to some point where the angle is going to be greater than 90. Is that possible? That's not possible. We can't have that. So the condition to find the maximum m value is to go ahead and set your angle to 90. So if we do that with the equation here, what we're going to do now is take that same equation and let's say to find the maximum order number is just a word for m, right? We're going to say that, I'll just reverse the equation. So m lambda over omega, we're going to set it equal to sine of 90 degrees. And in fact, actually, we can't allow this side here to exceed sine of 90. Otherwise, it doesn't make sense. It would be behind the screen. So in reality, this is not only equal to, it needs to be less than or equal to sine of 90 degrees. And now we can solve for m. So let's go ahead and multiply both sides by omega over lambda. And omega over lambda is a positive number. It won't reverse the direction of that inequality. And so that tells us that the order number has got to be less than or equal to, remember sine of 90 is 1, right? This whole thing is just 1. It's got to be less than or equal to w over lambda. W in this case is equal to 3 times 10 to the minus 6 meters. And lambda, we remember, is equal to 525 times 10 to the minus 9th meters. And so we can go ahead and cancel these two out. This comes out to a value of 5.71. So what's m equal to now? Is it 5 or is it 6? Remember this, it's always less than or equal to that value. When you calculate the maximum order number, you always have to round down. So m in this case is going to be equal to 5. If we're looking at the picture here, then what we're looking at essentially is something like this. So here's our m equals 3. We're only going to get 2 more in there. We have another order over here. There's m equals 4, and then we'll have one more that doesn't quite hit the 90. That's your m equals 5. And besides those ones, there's no other higher order numbers of m.